Okay, so this first video is just going to be kind of a recap of some of the things that we've done so far. So a first order partial differential equation is an equation that relates an unknown function and its partial derivatives, and its first partial derivatives. Okay, so you saw this in your ordinary differential equation class. The only difference here is that there are two or more independent variables, and so all of the derivatives are partial derivatives instead of ordinary derivatives. And again, the goal, just similar to your ordinary differential equations class, is given this partial differential equation and perhaps values of u, some other information like values of u along a curve, we want to determine the solution, or maybe even less ambitiously, determine properties that the solution has. So a solution to a PDE is a function that satisfies the equation, the PDE. The equation is this equation there. So in other words, you take the function, you take the proposed solution, you plug it into the function. If it's a true equation, then it means that's a solution. So similar to how, what does it mean for x to be a solution to x squared plus 1 equals 0, or I don't know why I did that, x squared minus 1 is equal to 0. It means that if you plug in x, if a number is a solution to this equation, x squared minus 1 equals 0, it means when you take the number and plug it into x, the equation is true. So for example, minus 1 squared minus 1 is equal to 0, so minus 1 is a solution. Of course, 1 is a solution as well. If I look at 2 squared minus 1, this does not equal to 0, so 2 is not a solution. Okay, something similar, it's the exact similar thing when we're dealing with equations or with differential equations. A function is a solution to a PDE if the equation is true when you plug it in. Okay, so a quasi-linear PDE is a PDE that has this particular form, a of x, y, u. It could be xtu. It's just going to be independent variables. It could be even more than two independent variables, times the x derivative of u plus b x y u times the y derivative of u is equal to some other function c of x y u. So if the equation has this particular form right here, it is called a quasi-linear equation, where a, b, and c are given functions. If a function has this form, so notice the functions a and b both depend on u. A semilinear equation is going to be similar, except a and b can only depend on x and y, or whatever the independent variables are. But the right-hand side, this function can still depend on u. That's a semilinear equation. And then a linear equation is going to be, a linear equation is an equation of the form. So the left-hand side is going to be the same. But on the right-hand side, this is not going to depend on u. So we're going to have a function of x and y, a given function of x and y times u, plus another given function just of x and y. So that's a linear equation. Okay, now linear equations are kind of the easiest to deal with. Semilinear, the next easier, and quasi-linear, the hardest. Quasi-linear, these are going to be where we have shocks and expansions and other interesting things that go on. Okay, so here's the general overall problem solving strategy when dealing with first order linear PDEs. So step one, I always am wanting to write it as a times the x derivative of u plus b times the y derivative of u, and again, instead of y, it could be t, is equal to everything else. Okay, so I want to write it in this particular form here. Okay, two, I want to find the Cauchy curve. Remember, that's kind of my terminology. I want to find the Cauchy curve. That's going to be the curve along which I know u, i.e. the curve along which information about u is given. Okay, so once I have it in this, once I do these two things, the next thing that I can do is write down the system of ODEs. Now, if I have my equation in this orange standard form up there, x dot is always going to be equal to a, y dot is always going to be equal to b, and z dot is always going to be equal to the everything else, the right-hand side of the equal sign. And remember that z of s is defined as u along the characteristics. Okay, and then our initial values, x of 0 equals x naught, y of 0 equals y naught. The exact form of x naught and y naught are determined by the Cauchy data. So for example, if I'm looking along the x-axis, y naught would be 0 and x naught would just be a generic x naught. If I'm looking along the y-axis, it'd be the other way around. If I'm looking along the line y is equal to x, I might have x of 0 equals x naught and y of 0 equals x naught as well. Sorry, thought I was going to sneeze there. Okay. Step 4 is to solve the system of ODEs. Okay, so why do we want to do that? The sort of one of the main things that this will give us, this will tell us what u is, what the solution is, what u of x, y is along each characteristic. So given a characteristic, we know it's going to start at some x naught, y naught, and given, s units along the curve there, or however you want to think about it, z of s is going to be the solution of u at that point. So we know what along each characteristic, we know exactly what u of x is. This is because the way we've defined z of s is equal to u along the characteristic. Okay, and the final step is to so step 5 is this penultimate step. And the ultimate step now is to sort of weave all of these characteristics together. We know what u is along all of the characteristics. Now we're going to weave these together. That is, like, practically what this means is, given a point in the plane, we're going to find the characteristic that it lies on and what the solution is equal to at that point. So step 6, given a point, I'm going to use my common notation, which is AB, because I'm using x and y for the characteristics. Given a point AB in the plane, find the characteristic it is on. That is, solve the equations a equals x of s and b equals y of s for x naught and s in terms of A and B. Okay, because I know that U of AB is going to be equal to Z of S, and this sort of depends on the X naught as well. So I'm going to erase that now. Okay, and then we'll just plug in these formulas for X naught and S into the Z of S equation, or the Z of S function, and that'll tell us what the solution is. Okay, that's the general outline. We will look at examples of using this general outline in the next several videos.